Hello. Okay, so we're here now. So I guess, hello. Email. Okay, hello. We are here now. I guess I got pretty excited the other day about this the idea of teaching computer science. So I'm making this video again. Made some videos a while back, but so this is kind of a lesson about computer science. So there's this quote. This guy Edgar Dijkstra, I guess. So, and his quote is: "Computer science is as much about computers as astronomy is about telescopes." So, science, we kind of know the etymology of the word science. It's like science is the field of like human knowledge or something. So the science of knowing. There's in something the scientific method people kind of try to explain the scientific method somehow. So the scientific method is you're making a guess about knowledge about something that just is like what in knowledge in the field of things that are true or false. Like you could drag Gödel's work into it, but that is another example of just something that exists and is true. And so science is the study of discovering things like this and through a peer review process, uh, finding a way to test the hypothesis and verify that something is true and it is part of human knowledge, the total sum of human knowledge. So we'll say that's what science is. Etymology of the word computer. So the word computer originates from the Latin word computere, so whatever. So to calculate, count, sum up, or think together, even. So computer. So a computer, initially, computer referred to a person who performed calculations. So the modern meaning of the word referring to an electronic device emerged later as these machines took over the role of human computers. So if there was a job for a person who was a computer, so a person who performed calculations often by hand, like if you know if keeping track of finances, like a bookie, the people need to a bookkeeper needs to be able to perform calculations, go through the calculations, make sure that everything is meticulously uh not mathematics really is a broader field, and it involves like many things that just are structures in the universe of logic. Just a structure in the universe of logic is just something that is, and computation refers more specifically to something that is a process. So in math it's an important thing to have a process like through time. You go through steps through time. At this point in time, then you go to the next step later in time, and you go through a process to see that to verify these things in mathematics, like the things that are true in mathematics. So the and computer so a computer meant a person. Often it was a woman. So and so people that is a true fact. So kind of start wondering about that. Someone needs to go through and make sure that everything is true and a woman. And people want to make things gendered or whatever. Just I don't know. I didn't come up with this personally. So and then there were very important people in the field of computer science, which is a computer or is a computer science is a it's a subfield of science mathematics. It's a specific uh, type of mathematics, engineering, science, performing computations. Then there was a very important person named Charles Babbage who made uh, the analytical engine was a mechanical machine for keeping census, keeping track of like numbers and stuff. So and Ada Lovelace was a British countess and mathematician who knew Charles Babbage and is considered by many to be the first computer programmer because she did work for the analytical engine. Was the first programmer. She programmed an algorithm for the analytical engine, and these were very important people in the field of computer science in the 1800s. In the 1800s, these were mechanical machines. Later, important people, very important people in the field of computer science, like Edgar Dijkstra. Edgar Dijkstra, Edgar Dijkstra did, very famous algorithms, things that are very famous, provable algorithms that are you can go through them meticulously, one thing at a time, and see that they are true. You can verify, to be able to verify provability and correctness. So in mathematics, it's kind of like people want to drag Gödel into it, but there really is not a way to be incorrect. Mathematics is like the field of provable logical structures that just exist in logic space or something. And computer science has to do with the study of. So here we go. Computer science is the study of computation. Computation is, and we say any type of arithmetic or non-arithmetic calculation that is well defined, provable, true. How you say, it's like a structure in logic space that just is something that exists somewhere in like in an information space that's like a true logical thing that exists. And mathematics really goes far beyond, something like arithmetic. And a lot of these things are not algorithmic. They're not something that you would go. They're just like a logical structure somewhere in logic land. But common examples of computation, so mathematical equation solving, and the execution of computer algorithms. So that just like going through something through time, step by step, this step, this step, this step, and that's proof. Proof in mathematics is something you learn about. It's an example of like going through something step by step to verify a logical truth. Information, it's sort of an abstract concept. So information, we're in physical reality. We seem to be in space. There seems to be stuff in space around us. We seem to be in space, and time seems to be going by, 1 second per second or something, and things are just like going through time. Things in space are just going through time 1 second in a second or something. And information is an abstract concept for something that is not. It's not part of physical reality. It's like in logic land or something. And automation. So the Industrial Revolution, automation. The idea of like a machine that just like handles stuff, helps us, handle stuff, do stuff. Tool making becomes like the Industrial Revolution, and all the things that So then people say, well, what about being a human being? Like, yeah, and people try to say, there's no ultimate like right and wrong. Well, we're human beings. Like, yes, there is. Kind of. Computer science spans theoretical disciplines. So theoretical computer science, and that's exactly theoretical computer science. We're talking about the science of computer science, so a computer is really a machine, and that's like the kind of a very important like, what is a computer? Like, it's really incredible. Like, what is this? Like, I moved the mouse. Like, what? That's really an incredible, like, what? So, but computer science is like that's an application of computer science, applied disciplines. the engineering of an actual computer machine. And so like what that's really weird. Also, and computer science is, so the theoretical disciplines, algorithms. So an algorithm is like a step by step, algorithmic, it's something. An algorithm is like a proof in mathematics. An algorithm is it's like a proof in mathematics, like. And so like this picture here is a flow, kind of a, it's called a flow chart. So you have like your mathematical stuff, like you have these different things where you check. So this flowchart seems to be, you have your inputs like R and S are in the natural numbers, is S zero, and then you check like is S zero, and you go if it's true or false, and then you have the concept of looping. Looping is super important. Uh, so the theory of computation, arithmetic, like what is arithmetic, and also there's kind of this idea. So in physics, there's this idea. People really study physics and know what they're talking about. Like I really haven't, but there's some idea of like the smallest things, and everything's like built up out of the smallest things. So in arithmetic, what would those things be? So if multiplication, addition is like you're going one way on the number line, subtraction is you're going the other direction on the number line, multiplication is you're looping over addition. Like 4 times 3 is 4, and then you add 4, and then you add 4 again 3 times. So you're looping over addition 3 times. Then addition is like you're adding 4. So you're looping over 1. You're adding 1, you're adding 1, you're adding 1, and you're adding 1 4 times. You're looping over incrementing. You're adding 1. So for addition, you really only need incrementation, and for multiplication, you really only need addition, and then you need a concept of loops, and then you need a concept of it. How do you know when you're looping, and how do you know when you need to stop? And so you can say like, is S0 true or false, and then you know whether to loop or not. And so the theory of computation. So computation, like what is computation even? So I kind of am saying like, for computation, like, do you need addition? Like, no, you need incrementation and you need looping. And do you need multiplication? Like, no, you build it up from there. For multiplication, you need addition and you need looping. And it kind of continues from there. So, and information theory is, so if information is like, information theory is kind of like, okay, well, if we live in physical reality, we're in space, there seems to be matter in space, time seems to be going by 1 second at a time. And so and information theory is like, well, what about all the stuff that's so important that like that is not it's not real, like, right, like right and wrong, like that's so important, but why is it's not real, but it's information, and it is like, it's more important. It's kind of like in physical reality there's all kinds of like physically real things, and in information theory sometimes there's something that's just more important and it's not part of physical reality, so is it not real? And it's weird, in physics there are things that this does apply to, like gravity does not seem to have a particle that goes with it. Gravity seems to be a byproduct of other stuff. So is it real? Like, no, it isn't, but it's super important. Like if your gravity is just like a fictitious force, so you're going to take a long walk off something steep, like you're going to find out how important that is in physical reality. But gravity is something like in logic land. It's like it's not particles. Like that's weird, but true. And so applied disciplines, engineering, don't fall something tall, like that's super important. Applied disciplines, in information land, in logic land, and gravity kind of is not a good example, but there's other things like that are very good examples. Like so arithmetic, arithmetic, like knowing addition, subtraction, multiplication. But those things are in logic land. They're not part of physical reality, but they're super important. They really are very important things. And people say I never use those. Like, yes, you do. You use those. Like, you kind of right. And when you really study this stuff, you will eventually see, oh, I do use that stuff. Well, like, that's weird. So this so including the design and implementation of hardware computers and software. So computers are like they're machines, like that's engineering is very like they are, and hardware and software are a distinction. Hardware is in physical reality, software is not in physical reality. It's in information land, it's in logic land. It doesn't exist, but it's something that exists in logic land and runs on hardware in physical reality. So and these are very important, hardware and software, and the distinction is usually very important. Like there's concepts like electronics that's just hardware does not it kind of does it have software? Like no, maybe not really. Like it kind it like depending on where electrons are flowing, it really matters what the hardware is doing, and the information of what the electrons are doing and stuff is kind of it's not the same idea, but it kind of like so what but hardware is something machine in physical reality. Software is in information land. It's information in information land that's meant to run on the computer hardware. So so that gets us to the language that I want to present in this lesson, and this is kind of unfortunately named it's unfortunate kind of unfortunately named. This guy decided to name it this way. There's this idea. There was a man named Alan Turing, who was really extremely. He's considered probably the most influential guy in computer science. Like, what is a computer? What is computer science? Like what I was just telling you about. All you need is incrementation. Alan Turing is the guy who discovered stuff like that. And so there's this idea of something being Turing complete. What are the things that you need if you just have the bare minimum to do computations? What are the things that you need? So you don't need addition, you don't need multiplication. You do need a concept of incrementation. You need to be able to add one to a variable. You need to have a data pointer. So you need to have a way to have a number. You need to have a way to add one to the number, and you need a way to loop and stuff. But you don't need a concept of addition. You don't need a concept of multiplication. Those things are built up from more like lower level. Like they're built up from stuff. They're built up from smaller logical units. So like addition is something that is built up after you have your Turing complete system. So and it's this language is an unfortunately named language. It's just like an esoteric. What does esoteric even mean? Esoteric or something. So it's like people want to say it's esoteric, but uh, to show this is an example of a Turing tar pit. A Turing tar pit is an idea of like what if something is Turing complete and does not have anything else to help you out with anything. Like, are you ever going to be able to get to the point where you're moving a mouse and the mouse is moving? In a Turing tar pit, it is possible, and it's not. So it's very possible, and it's not something that you would ever kind of get to. Kind of like you kind of. It's very possible, and I shouldn't say that. Like if the Turing machine was fast enough, and you just had a Turing machine, and you just had a way to keep building more stuff, like yeah, you could just use a Turing machine to get to do exactly what this computer is doing. This computer is not. No physical machinery is a Turing tar pit. Like that's like, I mean, the initial computers, like in the 1940s, that everybody, they probably were Turing Tar-Pit machines that were just Turing complete machines and could do incredible stuff. I mean, so but so later in 1993, this Swiss student said, "What if I made a language that just is a Turing Tar-Pit? Like that's an interesting idea." And so it is. It's an interesting idea. It's a good thing. It's kind of an interesting thing to look at. And really, he kind of did. In my he. I guess it's almost my opinion. He has 8 instructions. 2 of the instructions are for input and output, and so these are for the machine to actually be used for something. And so in a Turing complete, so do you need the 6 symbols, or do you need these two? Do you need these 2 symbols for input and output? Like, yeah, you kind of do. What is a computer even supposed to be doing? So the idea of this language is you just have your list of numbers. So, and the way that this machine is set up is they are byte cells. So, at least 30,000 byte cells. They're all set to 0 initially. Then you have a data pointer, and you can increment the data pointer to go to the next number to the right, or decrement to go to the next number to the left. And you can add 1 to that number, or you can subtract 1 from that number. You have a data pointer that can move. It's like a tape. You have 2 tapes. You have your data and instruction tape. So you have your instruction tape that's a list of these symbols, going through these symbols. The instruction tape it's an instruction tape that has 8 possible things on it that are, and these 2 are for interaction with human beings, or input and output, interaction with the rest of the universe. These 2, arguably you need those for the machine to be doing anything, to be interacting with anything outside of the machine. And so why are you saying that? Like, if there's 2 tapes and you can look at both tapes, why are you saying this? But you are. So, and that also kind of makes it's something that, what is, um so input and output, pragmatically, what are we doing here? Like, I'm moving the mouse and the mouse is moving. So you need these 2 instructions. And so but then the machine has 2 tapes. There's a data pointer on a data tape, and an instruction pointer pointing to a certain point on an instruction tape. The instruction tape only has these 8 symbols, one symbol after another. The data tape has the list of numbers. It's a list of numbers. The data tape is just a tape full of numbers. So when you increment the data pointer, it's like you wound the tape forward 1 number, or wound the tape back 1 number. Increment and decrement the data pointer. Increment and decrement the number at the data pointer on the data tape. You add 1 or decrease 1. Then this is the concept of looping. Once you have looping, now if you can cleverly arrange these things, you can have a data pointer where you increment 4 times. So you've set the data pointer to 4, and then you increment your next one to number 3, and then you loop based on the byte that is set to 4. You loop that many times, adding 3, and then finally, and you have a third data position where you're keeping an accumulator, and you add up 3, 4 times, and so you've multiplied 3 times 4, you get your answer 12, and you've constructed multiplying 3 times 4 out of just these basic kind of like atom or smallest informational things that you can do not in mathematics, but in a sub space of computational mathematics. So so it's like you've gone through these one step at a time and have constructed 3 times 4 equals 12 out of just these things. And really, did you need these for that? Like, it's sort of, I mean, what's a computer? You know, like you're in a computer is a machine, so you kind of like this. So this is like input and output for the machine to interact with the rest of the universe. And really, if you have the tapes and can look at the tapes and you can watch the tapes going through the machine, and you're kind of like, so I mean, so this somehow is very important because if you don't have these, then you can have this incredible computer that's doing these incredible things, and somehow this concept of interacting with the rest of the universe is important enough that these two symbols need to be part of Turing completeness, the idea of Turing completeness. And so here's some examples of here's an example of so yeah, this is an example of a program that's adding 2 and 5. So we set cell 0 to 2. First we increment it once, then we increment it again. So it's that we've added 1 to 0 2 times, so now that equals 2. Then we shift over to the cell next to it. So we've set cell 0, now we're setting cell C1, and so then we increment 5 times. And so then let's see. So then we start our loops with our cell pointer on the loop counter. So let's see. So our loop counter is we've decided that let's see. So yeah, so we're starting our loop with our cell pointer on the loop counter. And our loop counter, we moved here to cell C1, and we are on cell C1. Now the first thing in our loop is we go back to cell C0 and add 1 to cell C0. So now we've added 1 to cell C0, and then we move back over to cell C1 and we subtract 1 from it. And then this the loop in this language, so the loop keeps going until this loop so the loop these need to match. For every one of these there needs to be one of these. So if the byte at the data pointer is 0, then we exit the loop basically. So if the byte at the data pointer is 0, then instead of just moving on to the next thing in the tape, we jump forward past this to the next one past this. And then when we get all the way over to this, if the byte at the data pointer is non-zero, if the data pointer is not 0, then instead of moving the instruction pointer forward to the next command, the next thing after this on the tape, we jump it back to the one right after it. And so so here so when we first do this, we're looking at cell C1. Is cell C1 0? No, it is not. And so we continue with our loop. This is we go back to cell C0, add 1 to it. Then we go back to cell C1 and subtract 1 from cell C1. So after we've gotten here, we've decided to start because cell C1 is not 0. And we've gone through this, run this once, and we've added 1 to cell C0. So cell C0 is now 3. Then we've gone back over to cell C1. We've subtracted 1 from it, and now cell C1 is 4. And then we go here. So now our loop, if we end our loops with the cell pointer on the loop counter, so that's the loop concept of loops. That's already gotten confusing. That's already gotten really confusing. And so, so basically this loop continues until C1 has added 5 to 2, and when we've gotten to that point, cell C1 is now equal to 0. And so when we finally get to this and we see, oh, cell C1 is now 0, so we end our loop and we continue. So, and then, so let's see. And so what we've done here, we've decided that, so basically we've gone through this and we've gotten to the point where we've added 1 to cell C0 5 times. So 2, we've added 1 to 2 5 times. So now cell C0 should be 7. We kind of know this. We've gotten lost now, but we know this. Cell C1 is now equal to 0, and we've decided to exit our loop. So cell C0 is now equal to 7. Cell C1 is equal to 0. If we had the whole machine going and really slowly, we could watch the little thing tick by, and it would be kind of interesting to watch both tapes moving and stuff. That would be cool. And then so to display we don't do this. We're not doing this yet. We're not displaying the character 7. We're not showing the number 7 yet. But we know, like in our, we just know, like we've gotten very lost now, but we know that cell C0 is equal to 7. We know that cell C1 is equal to 0. And so now we set cell C1 to 8. We increment it 4 times. I think the guy notates this so that it'll be, he's trying to make it more clear, but it's not going to be. Cell C1 is equal to 8. We've added 1 to cell C1 8 times. Now cell C1 is equal to 8. We're hoping. So, and when we go, like, we have to, like, if there's a mistake in this, we're just, oh man. And so now we have another loop. We have our loop. And so C1 equals 8. C0, we're hoping it's equal to 7. Now we're starting our loop again. And we're at now, so we've done this. We're moving over to what we're doing here is multiplication. This is interesting. And so multiplication is a loop over addition. Here we're performing addition, a loop over incrementation. Here we're performing multiplication, a loop over addition. And so we're adding 6 to C0. So we've moved. So this we set cell C1 to 8. We're starting a loop. And when we start our loop, we're seeing. So first we say, is C1 equal to 0? Well, C1 is equal to 8, so it's not equal to 0. And so then here we move back over from, and that's such a funny, like, well, let's see, and that machine, the machine can't, that's how the machine, like, thinks, It's like, well, let's see here. Is C1 equal to 0? Well, C1 is equal to 8, so it's not equal to 0, so it's not equal to 0. Like that, and so it's like a machine. That's funny, but yeah. So like, let's see, like, how many fingers do I have? And you say, well, here's 1 finger. Let's see, that's 2 fingers. And so it's like, it's not funny, It's like it's so like, no, it's not funny, And so, so then C1, we move cell C1. We moved over from C1 to C0, and we are adding 6 to cell C0 now. So cell C1, let's see, cell C1 equals 8. Cell C0, oh, we've kind of gotten lost now, but cell C0 equals 7. We know we did that before. So we add 6 to cell C0. So we're adding 6. We've incremented cell C0 6 times. So from 7, we've added 6. So that would be, 13, I guess. So now cell C0 equals 13. Now we move over to cell C1, and we subtract 1 from C1. So now this is equal to 7 now. We've subtracted 1. And then we get to the end of our loop. Is this equal to 0? Like, no, this is equal to 7, I guess. And so we do our loop and keep going. And we add 6 to C0 8 times. We loop over adding 6, and that's already 7. That has been 7. We did this, and it was 7. Now we're going through this. We're adding 6 to that number. We're adding 6 8 times. And each time we subtract 1 from C1, which is 8. So we go like we add 6 1 times to get 13. Then we add 6 another times, we get 19. Then we add 6 another times, and we get, let's see, 25. Then we add 6 another times, we get 31. And then we add 6 another times, we get 37. Then we add 6 another times, we get, let's see, 43. Then we add 6 another times, we get 49. Then finally, we add 6 one more times, and we get 55. And so now that variable in C0, the number on the data tape at position C0 is now equal to 55. And C1, we've been using C1 in our calculation, and now C1 has finally equal to 0, and our loop ends. And then here we move back over to cell C1. We go back to cell C1, and we print it out. This is our symbol that we were like, do we need this symbol? And I think now we do need this symbol finally, because we want to know, like, what's the final number? Then the machine tells us that the final number is the number 55. Oh, which is an ASCII value for the number 7. Like, why did we do that? Oh, that's weird. I don't know. For some reason we wanted to display it in ASCII, I guess. So I guess the ASCII value 55 translates to 7. Just like so here, the guy told us he was trying to communicate to human beings. We're the human beings. And so he was telling us, hey, ASCII is a standard for human beings. Like, the computer doesn't care, but ASCII is a standard for human beings. And so we'd done this. We actually did this. This was just the computer thinking by itself, and we got the number 7. And the computer was like, well, but I'm trying to communicate with human beings, I guess. And so the human beings added all this other crap. And so then that's a good example. This is an example of like we just want to add the numbers 2 and 5 together to get our answer 7. And so we had our answer 7 here. It was in variable C0. The variable C0 was equal to 7. But then we needed to communicate with human beings. And so ASCII is a American Standard Code for Information Interchange. And so it has and ASCII is a system where byte values correspond to characters. And the machine does, like, the overcomplicated computer machinery, like the machine for being a computer in engineering, there's such a thing as the byte value that's displays as the number 7. And so if we had any number in these cells, what we got to do is add 48 to that value. So when we add 48 to those values, we convert our digit, whatever the answer was, like 0 through 9, whatever our decimal digit answer. Like, the computer 100% does not care about stuff like that, but the human beings do. And so we've done all this other stuff, including this instruction. For some reason, we decided this instruction is important. Like, we really decided that, and we all agreed on that. And so, and this too, we all decided that and agreed on that. So I guess we did all this extra stuff to make sure that it will print out a little glyph on the screen that is the number 7. Like, we wanted to do all that extra crap, and we did. Like, why did we want to do that? And so, like, the computer. Well, what's a computer even for? I mean, so that's, I mean, that is that. So the computer is for, first we did our calculation, and then we done our extra crap here so that we will get our answer printed on the screen. And that is like for the engineering aspect of like, well, why are we doing any of this? And so uh this is all, actually that's a really interesting example here. This is an example of the computer is doing a computation, and this is all engineering. After that, everything is engineering. All of this is this code block here is the engineering side of the computation. And then our hello world program, that's interesting. There's a hello world program in this language. That's an interesting example. uh, and so hello world is often, you know, in a programming language, the first thing that you want to be able to do is, in the programming language, you want to make sure that you can get the programming language to say hello world like that. That's a common exercise for the class. Which, if you really want to use this language, like, there's all kinds of reasons that you actually do not want to use this language. Uh, it's a really interesting example of, like, if you only had what you barely needed to do a computer stuff, like, what do you even need? And arguably, you need these 8 symbols, including these 2 symbols. And so that's, you know, computer science. So in computer science, so yeah, okay. That, I guess I'll just, I don't know. No reason for me to keep talking. Hey, let's see here, man.